Okay, so we said that we have a very simple crystal with a central atom that is going to be positively charged for simplicity. This is kind of an ideal high symmetry configuration of the crystal where the polarization, meaning the displacement of the central atom with respect to the center, is zero. Okay, and we have also hypothesized that this crystal would actually rather be either like this with a positive p, which quantifies the distance that the central atom has moved up, or like this with a negative p, where these two p's are equal in magnitude. These two states are equivalent. Okay, so of course in physics, to start making arguments and calculations, we have to worry about the central quantity when we discuss all this, which is the energy. So essentially here we have one relevant variable, which is the p. Let's call it polarization for just to make things more specific, but it could be something else. It could be a different structural distortion that is not polar, for example. But okay, let's call it polarization. And we would like to express the energy of this crystal as a function of the polarization, right? I mean, so we want to find an expression for the energy as a function of P. And for the moment, let's imagine we are working at 0 Kelvin. At 0 Kelvin, there are no vibrations. We are neglecting 0 point or quantum mechanical effects. So the atoms are simply dots in space. They are not wave functions. Okay. And so I can perfectly well consider three different states, one like this, one like that, when I put this atom in the center, even though I know that one is not very favorable, and one like that, and wonder how does the energy look like that would connect these three states. Okay, so the energy is a function of P. Okay, so to write the energy as a function of P, of course, again, in general, this can be very, very complicated, but what we are going to do is to write the simplest energy that we can imagine as a function of the polarization, but one that is compatible with everything we know about the problem so far. Okay? So about the problem, if you think about it, we know quite a few things, even if we don't know anything about ferroelectrics or structural phase transitions. I guess it's not very difficult to convince oneself that one thing that we want for this energy is that these two states, which are equivalent, essentially they are the same, but transformed by symmetry, so to speak, these two states have to have the same energy. More generally, if we imagine that we start from the state in the middle and that we move the atom up by an arbitrary quantity versus moving it down by an arbitrary quantity, we want these two energies to be related, right? So essentially we want the energy to be even as a function of the polarization. So E of P should be equal to E of minus P. This is very, very intuitive, right? It comes from the fact, in a more deeply, what we are doing here is to look at the symmetries of this high symmetry configuration, which in particular has a mirror plane, let's say here. Okay, and we are intuitively using the notion that if I consider any state of this system with a certain value of P and I apply the mirror plane, so the mirror plane, you see, will take this negative P to this positive P, right? If I apply the mirror plane, I have to end up in a state that has the same energy. So here the subtlety is that we are applying a symmetry of the high symmetry configuration. These two configurations don't have that mirror plane. But it has to be true that for any low symmetry configuration I can generate, the mirror plane gives me another one. The mirror plane that is broken gives me another configuration that has the same energy and is equivalent by symmetry. Okay. In this very simple example, this seems trivial and very intuitive. In more complicated examples, the rule continues to apply, and then you can get less trivial conclusions out of it. Okay, so we know that this has to be an even function for the polarization. And now, if we try to get the simplest expression for the energy, what do we know about this energy, or the simplest form of the energy? Let me make a bit of room. We know E of P equals E of minus P. And imagine I try to plot the energy as a function of P. So we have argued that the energy is minimum in configurations like this or like this. So that's where the system goes at 0 Kelvin. So this pretty much means that if I try to draw this, over here I have to have a minimum, and over here I have to have another minimum that is perfectly symmetric. So that E of P equals to E of minus P is satisfied, and I have two minima for non-zero values of the polarization. From our hypothesis, this is what has to happen. And then what happens with the energies in between? Well, there will be many ways to join these two lines, always satisfying this. Like, for example, we could imagine that this is like this. If this is like this, by the way, then this will have consequences on the transition that we see later with temperature. But we are not going to go there now, because there is a simpler way to join these two minima, which is, of course, simply to go through a maximum there. It doesn't get simpler than this. We have two minima, and we want to complete the energy in the places in between with a smoother possible function. And that's by having a single maximum in the middle. And then, of course, when we write this, or when we draw this, now we can try to give this the simplest possible mathematical expression. And when we see a curve like this, we pretty much know that then E of P should have more or less the following form. If you see, this condition means that, well, how do we find a simple form for this function? A very practical approach is to imagine that I start from the energy of the high symmetry configuration, which is 0, by the way. Well, I can choose it to be 0. So let's choose it to be 0 for simplicity. And then I expand, I Taylor expand as a function of the polarization. Of course, Taylor expansion seems to imply that the polarization will be small. Here, let's use this just as a mathematical, the simplest mathematical form that this energy can have, that then will allow us to make calculations. Okay? But if I imagine that, if I think of this as Taylor series, the first thing I would have here is the derivative of the energy with respect to the polarization, evaluated at 0, multiplied by the polarization. Right? But this is quite obvious. This will be a number. If there is a term like this, then it will mean that this condition is violated. If I have a linear term, or in general, if I have terms with odd powers, the function is not even, right? So this already tells me that this derivative is 0, which was intuitive, of course, or was already there in the curve I drew, which is compatible with having an even function. So it means that here I can only have even powers. And if you think about it for a second, the two even powers that I need to describe something like this, so the simplest possible theory I can construct is one where I put here something like 1/2 alpha p squared, and here 1/4 beta p to the 4. Okay? So this is incredibly dirty, but let me clean it up a little bit. Okay? So this expression, which for simplicity we are going to remove the energy of the high symmetry phase, let's assume it is 0, gives us the simplest possible form for the energy as a function of the polarization. It's a double well potential, which is of course the thing that probably you have seen over and over again if you have read about these things. Okay, questions? We can stop it.